Welcome. Let's talk a little bit about least squares and a few other things. So in this video, I'm going to talk about the homework that is due next Wednesday, as well as what are orthogonal spaces and then quote unquote the best solution. So first, let's address homework. Our homework number 9 is due on Wednesday, November 22nd. That's the day before Thanksgiving. Here are 3 problems about linear transformations. Go ahead and screenshot this or whatever to go ahead and do this. You're going to determine if something is a linear transformation, find the matrix of a linear transformation, and then prove that something is linear transformation just based on some general information. All right, so those are the 3 problems. Please make sure you get those done. Now let's talk about orthogonal spaces. We've talked about orthogonal vectors being orthogonal to each other. A vector is orthogonal to an entire space if it's orthogonal to every vector in that space. The really cool part is because a subspace is made up of its basis, all we have to test it against is the basis of that subspace. So we can say that a vector not only is orthogonal to another vector, but we can say it's orthogonal to a vector space. This is kind of cool and really powerful. So if I know that a vector is orthogonal to a vector space, then anything in that space already I know it's going to be orthogonal to. Oh, I don't know what happened there. Sorry, my apologies. Now, a set of vectors that are all orthogonal, if I talk about all the vectors that are orthogonal to W, so W is a vector space. If I say that we talk about all the vectors that are orthogonal to W, those in and of themselves actually make up their own space called an orthogonal complement of W, or denoted W with this little like upside down T, or as you may recognize is a perpendicular symbol, because perpendicular, as you first learned it, was actually orthogonal. Orthogonal is a more general version of perpendicular. So we now have a really cool concept. Now, the reason I'm bringing this back up is to tie something about some important complements we've already dealt with. If I give you a matrix A, it doesn't matter if it's square or not, but the complement of its row space is its null space. In other words, if I take anything that's null space and I take the dot product of that with anything in the row space, the two of those two things will quite easily give me 0. If I take the dot product of any column with anything in the left null space, their dot product will always equal 0. And complements are symmetric. So the complement of the left null space is the column space and vice versa. The complement of the null space is the row space and vice versa. So that's how we get all this. So this is the really cool part. We can actually tie this together to concepts we already have. Now, that actually does come play a little bit in least squares, but I'd have to introduce some more details. But that's an idea I want to just lay because we're going to talk about some other things, and it does tie back in just a little bit. All right, so let's move on to a question. So I want you to think about this for a second. Suppose that I have a matrix equation, AX equals B, and it does not have a solution. From what we've already talked about, that actually means that B is not in the column space of A. It's no linear combination of the columns will give you that thing. So it doesn't live in the column space. Well, where does it live then? And how can we find it? Because if I can't solve this, the question is, can I find something really, really close? So in this class, maybe you're like, well, I don't care. But if this is a real world problem where I have a system of equations and I want a given solution, given output, I need to figure out what that input is. Or in other words, how's the closest I can get? Maybe I'm not actually going to get all the way to B, but I'm going to get pretty darn close. So how do I find the best solution? This idea, and we will call it X sub B, is my best solution. The B is for a couple different reasons. We're going to say that to find the closest thing, I'm just going to call P is actually something in the column space of A. So I'm saying, what is the closest thing in the column space actually to B? And now we're going to solve that. Now, again, that B is just a reminder that 1, X sub B is related to the original, is not the original X. And 2, it's the best solution. Yes, I am playing with words here. So the B is for best solution. So we're going to use this little subscript of X sub B to denote the best solution. And this P is closest thing there is in the column space of A to B. Now you're probably like, okay, so how do I figure that part out? All right, we'll get there. So we can capitalize on something that those you took Calc 3 may remember. We can actually do what's called projecting a vector onto another vector. By the way, in Calc 3, you did this, and it worked for a 2-dimensional space or even 3-dimensional space. It turns out it's true for n-dimensional space. So I can project a vector onto another vector. Now, meaning if I have some vectors, just kind of draw this real quickly in 2 dimensions. So if y'all get the idea. If I have this, suppose I have this is my normal 3-dimensional space. So this is my X, Y, and Z axis. Well, let's suppose that I have a vector here, and I have a vector over here, and I have a vector that's coming right up into space. Let's call it here. If I want to take this vector in space and I want to bring it down to this plane, it's going to project down onto this new vector in the plane. That is actually what we're going to do, is we're going to bring it down onto a plane, or in other words, we're projecting it on a line that's made up from A. I hope that makes sense. If it doesn't, don't worry. The projection idea is just an idea from calculus. You can take calculus and learn a little more about this. But the idea is we're trying to project one vector X onto another vector A, and it creates a vector P that's actually on the line that A makes. So it may be further down A, but it's going to be somewhere in what A is all the things that A creates. All right. Now let's call P this projected vector. Now you see why we picked P is because it's a projected vector. And since P lines on the line of A, that means it is some scalar times the vector A. We'll call that alpha. All right, so now we need to show the following. That P alpha A is equal to this ugly, nasty mess here. Yep, I'm whistling. This is actually alpha. And notice that is A, the vector A transposed with X. This right here, for all of you that forgot, this is the same thing as saying A bar. That wasn't A bar. A dot X, where I do the dot product. Because the dot product, you have to transpose the first one and do it. If you transpose the second one, you get a matrix, and that's not good. So here, this numerator is going to give me a number. This is going to give me a number for the denominator, which actually tells me that this is going to give me a solution. Be careful. These A bar transposes do not cancel out. Do not cancel them out. So we're going to find a vector E, that's our error between X and P. And A and E are both orthogonal to each other because E is gonna I want it to be somewhere. So the way to think about that is if this is A, this is the vector P. Sorry, this is the vector X. Do that. Then when I project that down, it's going to project down and it's going to give me this thing, which is going to be P. Well, this vector right here is our error vector. So it's going to be orthogonal to A because that's how I get from X down, directly down onto A. That's what the projection is really doing, sending it straight down onto it. Okay, so with this in mind, let's kind of visualize this for a second. If you take this system of equations, -1, 2, 1, -2, and you try to solve this, it will not work. You can go draw, play with GeoGebra, go do whatever you want to visually see this thing. Go ahead and pause the video and go do that. But you can see that this isn't possible. But we can see that even though B is not in the space, the line -1, 1 is in this space. And so we're going to call that, because notice that's the first column. It's going to be in its, obviously it's in there. And also notice it's a product of the second column. Second column is a scalar. In fact, my columns are scalar multiples of each other, which dramatically impacts a lot of things. All right, so because of this, this negative 1, 1, not only is it our first column, it's actually the entire basis of the column space. So B is not in this, which is just the line times some scalar. So with that said, I want P to be the closest point on B that's closest to the column space. And the shortest distance lies on a line perpendicular to A. So E equals B, my solution I want, minus P, be the vectors whose distance is B to P. Well, since it's orthogonal to A, I can dot product it or multiply by A transpose on the left-hand side, and it'll equal the zero vector. Well, since P equals A alpha, then alpha equals this from this relationship. Now, if all of you that don't get that, so in this relationship, this equals A bar transpose times B minus alpha A. And that's equal to 0. If I distribute, I get A transpose B minus alpha A transpose A equals the 0 vector. I take this, I move it over, and then at that point in time, I can simply divide by the A transpose A to get my final solution. So go ahead and play with that. If you don't believe me, look at it carefully. All right, so but since this is true, now if I multiply, this is a number, so I can multiply it on the left-hand side or the right-hand side. But if I do it like this, when I take this A and I multiply it up to the numerator, well, now this is going to be a matrix. And this is a number. So that's going to be a number times a matrix. In fact, it's going to be an outer product kind of idea. So it's going to have rank 1. This is where that rank idea comes back into. And this actually is our projection matrix. The key thing to notice here is that I'm multiplying A times its transpose. Well, so going back to our problem here, if I took XB, this is equal to something on the thing. So if I say it's equal to this, well, I got this number by simply saying, what is the scalar product, going back, that's closest to my original value? Again, I'm going to go back to my problem. I got negative 1, 2. Well, negative 3 halves, 3 halves, each of them is off by 1/2. That's pretty darn close. And so the solution, if you do this, is going to give you this. So everything is equal to this plus, now notice alpha, it's alpha times, well, the original, I just took a version of this, and the original thing I wanted, where alpha is any real number. This is not the same alpha. I probably should have picked a different variable to make it a little more clear. I was on a Greek roll. All right, so, and you can check that. Those are equal to 0. That's not an accident. All right, so let's try to generalize this in a situation that's not easy. That was a 2 by 2. We could look at it. 3 by 3, 4 by 4, 5 by 5, we can't visualize. So suppose I give you matrix A, where I have my columns are A1, A2, A all through AN. Well, if B is going to be in this column space, we have to find the closest space in it. And so again, we're going to say B is equal to A times some X. Now I'm going to do a star, but same thing as an X sub B. And any vector in CA is going to be orthogonal to this. So we can still do this whole situation. Now, if you're looking at all this, when I'm multiplying all these transposes over, this really, by the way, is this. It turns, because these are all of the columns that I'm transposed, well, that's because into rows, which meant this is really A transpose was all of this whole system with the B and the AX. Well, if I multiply that, it's A transpose B minus A transpose A. So this is A transpose B minus A transpose AX. That's a horrible A. That's what happens if I multiply it in here. I can move this to the other side. And what I find out, in essence, is if I multiply both sides by A transpose, it becomes something that I actually can solve. So this is kind of strange and weird, and it messes with our heads. And in fact, the solution, which is this, is because we're doing the inverse of a matrix and it's invertible. And how do I know it's invertible? A whole bunch of other stuff. I won't get into that right now. But let's look at an example. So let's let A equal 1, 1, 1, 2, 1, 3. You try solving this. Quick reduction shows that does not have a solution. You row reduce the left-hand side. I literally will, a quick row reduction would end up giving me 1, 1, 0, 1, 0, 2, 0, 1, 3. And then we can go from here. We can say, okay, row 2 times 2, take that away from row 3, and I will get 0, the last row is going to be 0, 0, 1. That's a problem. That means there's no solution. All right. So because this does not have a solution, I'm kind of skipping over that so you can play with it. I need to multiply both sides. So again, this is A, this is B. If I multiply both of them by A transpose, well, I get this nice, wonderful new 2x2 matrix. Multiply B by A transpose, and I'm going to get this. So I now just have to solve this equation where notice this is A transpose A, and this is A transpose B. And I have to solve for whatever my X vector I don't know. And it turns out this has a solution, namely -5/3, 3/2. So that actually means that this is the best solution to our original system of equations. So the idea here is that we can solve any system of equations simply and directly by multiplying both sides by A transpose when it does not have a solution. All right, good luck. Let me know what questions you have.